So which of these are vector spaces? Options 1, 2, 3, 4, 5 were pretty popular. 7, 8, or 9 people chose them. The least popular one was this: the limit is infinity or minus infinity. And only 2 people said that that was a vector space. In fact, that one is not a vector space. So the people who did not select that one, congratulations. Can someone tell me why that one is not a vector space? Yeah.
Because we have to see us suppose that converges to infinity.
Yeah.
We have the sort of negative sequence going to converge to negative infinity, but then if you add them, they're going to converge to 0. So it's not going to be a vector space.
Okay, so I like this. So this is let's make a little list. This is also, I think, what I kind of was thinking. Why are there no more pages? Can I get a third page? To hit new page. Okay, that's the pages. So this is like a list of bad things, right? If you do these bad things, then you are not a vector space. Bad things, and one of them is instead of bad things, let's be more positive. Let's say things to check for. Things to check, and one thing is closed under addition. Under addition. So if you have an honest-to-goodness vector space and you add up 2 things in the vector space, it better still be in the vector space. And you just gave me an example where you add up something that goes to infinity, you add it to something that goes to minus infinity, and the final limit will be 0. So not everything has this property, but even one example will ruin the whole closed under addition property. So the example is if you take the sequence, let's make an be the sequence n. So this is 1, 2, 3, 4, ... and bn is the sequence of minus n, so this is -1, -2, -3, -4, ... So an equals n is in our space because the limit is infinity. The limit of an equals infinity, plus infinity, and the limit of bn is minus infinity. But if you add them together, you do a big plus here, you get a new sequence cn, which is 0. n minus n is 0. So this is the sequence 0, 0, 0, 0. And the limit of the cn's is 0, and therefore not in the space that I said. So I said the set of sequences whose limit is infinity minus infinity, it includes an and bn, but it does not include cn, and therefore this space is not closed under addition. You can add 2 things to escape the space. So closed under addition is a good one to check for. I heard somebody else have a different reason why this one is not a vector space. Yeah?
I can think of a 0 vector.
Yes. Must contain a 0 vector. Okay, so there has to be an element. There must be some element that when you add it on to the other elements, doesn't change that original thing. So the sequence, the 0 element for sequence is, let's call it z sub n, z for 0, is the 0. So 0, 0, 0, 0, the sequence of always zeros. Oh, we already have a name for that. It's already called cn. Good, it's already on. 0, 0, 0, that is not in there. And if you don't have a 0 element, it can't possibly satisfy the properties of a vector space. So that's another one. So these are really good ones to check for. Very commonly, if it's not a vector space, it'll fail one of these. And that is why this one is not a vector space. Okay, the other one people were slightly less confident about is this one. The set of functions f from 1, 2, 3 to r. So only 7 people chose that one. But I will argue that that is the most common vector space that everybody studies and knows from real life and from linear algebra class. It's written sort of in disguise. So you're not used to seeing it like this, but it's actually exactly the same as a more common vector space. Does anyone know what the more common vector space is? That's exactly the same as the one I have highlighted. Yeah?
Is it Z mod 3?
It has something to do with numbers and it has something to do with 3. So you're very close. I think you said Z mod 3. Z mod 3. That is just the set 0, 1, 2 with certain rules of addition and so on. So that's kind of like the target space. But it's got something to do with 3 and it's got something to do with ordinary numbers. So you're on the right track. Anyone else want to take a stab at it? Yeah.
Is it R3?
Is it R3? So R3 is X, Y, Z triples, where each one is some number. X is a number, Y is a number, and Z is a number. Right? This is everyone's favorite vector space. Just any three numbers. Okay. This is the one everybody knows. Why do you not? Because space is like that, right? You tell me where a point is. Is the thing that I have highlighted, is it like that?
No.
Well, it's functions that input either the number 1 or the number 2 or the number 3 and output a number. So what do I need to tell you if I'm thinking of the set f going from 1, 2, 3 to R, the set of all f's that do this? What is it? Well, I have to tell you what is f of 1, I have to tell you what is f of 2, and I have to tell you what is f of 3, right? If you know f of 1, f of 2, and f of 3, then you know exactly what the function does. And those can be anything. They're numbers in R. Right? Why are they numbers in R? Because, like we said, the output is in R, right? So there's sort of a natural bijection. If you know the value of f of 1, f of 2, and f of 3, then you know the function f. So it's kind of 3 numbers. And that's exactly what R3 is, 3 numbers. So both of these things are the same because they're both lists of 3 numbers. Just how you sort of think about the 3 numbers is different. In one of them, it's like explicitly like, here's the first number, the second number, the third one. And in this one, they're kind of like wrapped up in the function, right? They're hidden inside the function as the 3 possible outputs. But these 2 things are exactly the same. Okay, it depends what you mean by the same. That's why mathematicians use words like isomorphic or something. But morally speaking, they're the same. The 2 sets, you can make a nice bijection between the 2 sets in the natural way, saying x equals f of 1, y equals f of 2, and z equals f of 3. Okay, so that one is definitely a vector space. So even though that was the least popular one, that is the most vector spacey of them all, and the other ones were all very, very popular, it turns out the other ones are all vector spaces as well. So if you selected all of them except the last one, congratulations, lots of people knew these ones. So all of these are vector spaces. To say that, what is a vector space? It's a very abstract concept. Anything that satisfies the axioms of a vector space, of having a kind of a vector addition and a scalar multiplication that work in the nice ways, that is a vector space. And let me copy down the definition from the actual textbook here. So what is the actual definition? Let me try something. So far, when we have math stuff to do, the blackboard is nice, but let me also try typing for things. Because sometimes my writing is less neat than typing, and we'll see how this goes. So you guys tell me if this is terrible, and we'll switch away. But I will attempt to type these things. So let's try. This is definition 1.2.1 from the textbook, and let me make it a bit bigger. Oh, it crashed. You know, that's a good reason to use the blackboard. Let's try one more time. Okay, wait. So the notes didn't crash, just the new one crashed. Interesting. Okay, we'll try one more time. Thank you for your patience. Okay, let's try again. So definition 1.2.1. This is the very first thing in the textbook. And can I zoom in so you can see it? Is it big enough? Yeah, that should be big enough. And it says vector space. A vector space is a set. I think in the book, I don't remember what they call it, but I'm calling it V. V for vector space with plus operation and a scalar multiplication operation. And what does it have to satisfy? It has a big list of rules. So one rule is that x plus y must be equal to y plus x. So if you add things, the order doesn't matter. Another rule is x plus y in brackets. So if you first do x plus y and then you add z, that has to be equal to doing x plus y plus z. So the order you add things doesn't matter. It has to be the same either way. Okay, this next one I found quite confusing. But it's in the textbook. And the thing about these vector space things is you can give the axioms in different ways that are equivalent. So I've never seen this way before, but this is the way they do it. And you need to know the qualifiers for this one. So the first two were for every x and y. I can add that in. For all x, y in V, this has to happen. And this is for all x, y, z in V. Any 3 vectors that has to happen. The next one is a for all there exists. So you give me an x and a y, and I find a z, and it's such that what? Such that z equals y minus x. And I'm putting minus in quotes because minus is not technically defined, right? So what could it possibly mean that z equals y minus x? What it actually means is that you rearrange the equation that x plus z equals y. So if you give me an x and a y, I must be able to find a z so that x plus z equals y. That vector z is also known as the vector y minus x.
Did you mean to make z in V?
I did mean to make it in V. Thank you. All 3 of them need to be in V. Yes, that's very good. Thank you. This is great. Okay. Okay. So this is a weird one, and the textbook does this one. A lot of other sources will have some explicit axiom about having a zero vector, just like we said. And there definitely needs to be a zero vector. That's like a real thing that needs to be there, but it is not on the axiom list. And the reason is this weird subtraction thing substitutes for having a zero vector, and that's because you can subtract a vector from itself. So in this one it says for every x and y there exists a z. If I make the same vector twice, so I make x equal to y, then I find a vector z so that x plus z equals x. And that vector has got to be the zero vector. So this axiom is doing some really heavy duty lifting. It's doing subtraction and also the zero vector. And if you read the textbook, they have a little paragraph that says, oh, by the way, this is how the zero vector works. Another question you might ask is, I said there has to be at least one zero vector. Maybe there's two zero vectors. And actually you can show that there can only be one zero vector using this axiom. So it's like some technical work, and that's what they use. Okay, so that's it. Those are all the like pure addition things. The other thing is we have a scalar multiplication operation. And so we have some set of scalars that we can multiply by. And in this course, the two sets of scalars will either be R, so real numbers, or C, complex numbers. And I think typically it'll be R, but sometimes it'll be one or the other. To combine both R and C, we use F. And F means either R or C, means either, depending on context. So to keep things very general, we're going to use F for now. F stands for field. In principle, you can do a vector space over any field, but fields more exotic than R and C will not appear in this course. Okay, what are the axioms involving scalar multiplication? They look like this. We're going to say if you do alpha times beta times x, so alpha and beta here are scalars. I can write that here. Alpha, beta are in F. Alpha, beta times x. So this is first multiply x, the vector x, by beta. I guess I should say x is a vector. X in V. Then multiply by alpha. Well, the order shouldn't matter. So that should be the same as doing alpha, beta, and then x. So you can multiply the scalars in any order. Very simple, as you would expect. And the next one says that scalar multiplication plays nice with addition. So you need alpha plus beta times x. That needs to be alpha x plus beta times x. And lastly, you need to have the property that scalar multiplication by 1 does nothing. 1 times x equals x. Okay, so those are the three properties that have to do with scalar multiplication. There are three properties to do with addition, and altogether, that's what a vector space is. All right. Questions or comments? Let's get a quick temperature of how you guys like the typing. Who thinks the typing is good for these things? Who is kind of like meh about it? Okay, let's try it a little bit longer, and then we'll see if we switch back or not. I thought I would try it since it's a little neater for things like this where we need a big list of things. When we do calculations, we'll definitely use the board. Okay, great. So yeah, if you want to see the stuff about the zero vector, right, this is definitely a true fact about vectors that we read off before, that there must be a zero vector that must contain 0. That is definitely a true fact, and it's discussed in the textbook how it comes from those axioms, but you can also use that as well. All right, the other concepts you need to know are things that come along with vector spaces are all these concepts from linear algebra class. Oh, maybe before I say the linear algebra stuff, I'm going to say what is a function space. Okay, we'll try the definition on here now. So definition, function space, and this is in the textbook as well. What? It's 1.2.3. 1.2.3. The next thing in the textbook is a function space. And what is a function space? It's a space of functions. So if you have f from A to f for some set A, this can be a vector space. So some collection of functions like this. So let's say some subset of this can be a vector space. And the reason it's a vector space is we know how to add functions together, we know how to scalar multiply functions, and therefore we automatically have a nice addition and scalar multiplication on the set. It's automatically going to satisfy a lot of the properties like the order and things because addition and multiplication on f already satisfied. And the examples are all the examples from the first mathematized question. The 5 mathematize examples. So if we go and we pop this back open, all of these things were actually function spaces. So they're all vector spaces, and they all are actually also function spaces. So polynomials, I think it's pretty clear how those are functions. These two are very explicitly functions. More polynomials, those are also functions. The last two maybe don't look like they're functions, because I said they're sequences. But if you think about them in the right way, they are also functions. So let me write this one out explicitly. So the sequence is n equals 1 to infinity, let's say such that the limit as n goes to infinity of an equals 0. That is some set. But you can actually write this as a set of functions. What kinds of functions would it be? What is the input? The output is going to be f, so it's going to be functions from somewhere to the field f. I guess in this case, let's pretend there are real value sequences. So let's make f equal r, such that question mark. So there, you have to tell me what is the input to the functions, and you have to tell me what is the question mark. Yeah?
The input would be the natural numbers with the relation being that any natural numbers related to the nth different sequence.
Yeah, exactly. So the key thing is that it's the natural numbers, because that's the index set of the sequence. So just like I said, you can have f1, f2, f3 for x, y, and z for R3. You can have f1, f2, f3 all the way up to f infinity. There's no actual f infinity. Okay, you get the idea. You get all the numbers. So the only such that you need is that the limit as n goes to infinity of f of n equals 0. Right? That is doing the limit is that written over there. So that is also a function space. And in fact, I think all of the examples in the course are going to be function spaces. Are there examples that are not function spaces? This is a good philosophical question I do not know the answer to. Is there a vector space which is genuinely not a function space? You have to clarify a little bit, because you can make it some dopey thing where like it inputs itself or something. So that's a good question. Are there interesting vector spaces that are not function spaces? Not in this course. I don't know if in real life. Okay. Oh, let me give you some examples also from the textbook. These are some common ones. There's curly C of omega. So if omega is a subset of r to the n, curly C of omega means functions from omega to r such that f is continuous. So that's a common thing that we'll be playing with in this course. And you might see in the wild, curly C means continuous. What happens if you add a k to it? So if you see curly C of 2, that means k equals 2. It's continuous and k times differentiable. So C2 is the functions that are continuous, and not only are they continuous, but you can do the derivative twice, and the derivative makes sense. You can also put k equals infinity. That would mean it's infinitely differentiable. That's the space C infinity. Okay. Yeah, and sometimes people use p for polynomial, but let's leave it off. This one is quite common. Okay, so that's it for function spaces. Questions or comments so far? Yeah.
Sorry, what is the actual definition?
Of what?
Just that.
Yeah, so somebody writes ck of omega. They're talking about the set of all functions.
I'm sorry, I'm talking about the definition of a function space.
Yeah, some subset. I guess this is, I wrote it kind of vaguely. It's some subset of functions. So some collection of functions that satisfy the property of being a vector space. Yeah, function space is one of those things, I think it depends how you look at it, right? Is R3 a function space? Well, yes, if you do your F1, F2, F3 thing, and if you just think about it as 3 numbers, then it's not a function space. So it is kind of just a way for your mind, not for the mathematics. Yeah?
Just to clarify, a function space is always a vector space?
A function space is always a vector space. Yes. Maybe I should be extra clear and say function vector space, right? Yeah. So I mean a vector space that consists of a bunch of functions. Yeah.
What's omega?
Oh, omega is any subset of Rn. So if you're working on, like in the last class, we were working on the interval 0 to 1, and we did those like PDEs with 0 to 1. So I would make omega 0, 1. But maybe you're working on a bar that is a rectangle. That's like 0, 1 times 0, 3. Then that's your omega. It's whatever space you're working on. Yeah. Okay. Okay, so loading up all our stuff from linear algebra, the other concepts that I won't give the full definition for, but that you should know, are things like linear independent sets, and dependent sets, linearly dependent. So we got independent, dependent, and with those, there's the concept of basis. So independent means, well, dependent means you can write the zero vector as a linear combination of the vectors in your set. So somehow they can all combine together, even though they're non-zero, they can all combine to give the zero vector. Linearly independent means they can't do that. And a basis means that they are linearly independent and you can get the entire set out of them. Maybe I should add, as a concept, I could add a spanning set, because a basis means independent and spanning. And spanning. Okay. And with basis comes the notion of dimension, which is the size of the basis. So these are all concepts that you've seen before in linear algebra class, and we're going to see them again here, but in the context of function spaces and things. So that's going to be the new part. And in particular, the really exciting thing in this class is the idea of infinite dimensional spaces. So let's go to the examples that we had before. So some of these examples are infinite dimensional and some of them are finite dimensional. This one, F1, 2, 3, we said is the same as R3. This is a three-dimensional vector space. How do I know it's three-dimensional? Well, I can tell you a basis of size 3, which is the vector 1, 0, 0, the vector 0, 1, 0, and the vector 0, 0, 1. There's no way to combine those vectors to get the zero vector, so they're independent. And on the other hand, by doing copies of those vectors and scaling them, and adding them together, I can get to any other vector. So this thing is three-dimensional. This one, f from 0, 1 to r, so that's a function space, all the functions from the interval 0, 1 to r, this thing is infinite dimensional. There's no way you can give me enough functions that I can combine them together to get any other function. You need to have sort of a function for every possible entry in the interval 0, 1, so it's infinite dimensional. Similarly, this thing, polynomials of degree at most 5, is like a 5-dimensional space because the polynomials 1x, x squared, x cubed, x4, and x5, those span the whole space, and there's 5 of them. There's no way to add them up to get the zero vector. 5-dimensional, but the set of all polynomials is infinite dimensional because there's no way, you don't know what the highest power in my polynomial is going to be. There's no way you can make a finite list that contains the highest power that I'm thinking of. So that one is going to be infinite dimensional too. And really, the whole course is really what happens, what goes insane when things are infinite dimensional. So keep your eye on that. So in this course, we care a lot about what happens when the dimension is not finite. And when it's not finite, there is no finite basis. And when there's no finite basis, all sorts of crazy things start to happen, which we'll get to some quite soon. Yeah, if everything is finite, then you're in linear algebra class. You can always write things as column vectors and work with just vectors, and then everything's fine. But in infinite dimensions, things get quite insane. Okay. Yeah?
Is there an important difference between an uncountable and countable infinite basis?
Yes. So it turns out there will be, and we'll see that sort of organically as we go. It's really hard. I think once you leave finite, it makes sense to say the dimension is 7. That's perfectly fine. Saying that the dimension is either countable or uncountable is kind of like hard to put your finger on. So it's not only is it difficult, it makes sense to say if the dimension is finite or not finite. It's kind of hard to say if it's uncountable or not. And then you start getting into all sorts of complicated issues. So it really does get a lot more difficult as soon as you leave finite land, which is why this is the whole course. Yeah. Great question. Anyone else? Okay, so these are all concepts we've seen before. Okay. And I have some examples. What was the next question I had? Okay, yeah, this is about norms. We're going to get to norms in a second. Okay, ignore that for now. Okay, so, great. Yeah, okay, so the next thing I have is we are upgrading from vector spaces, we are upgrading to normed vector spaces. Let's start a new thing just for this. Okay. Normed. Normed vector spaces. Okay. And what is a normed vector space? It's a vector space plus a norm. Vector space plus a norm. And you have to know what a norm is. So a norm is some function. It looks like this. So they write it like this. X. You input some vector x, and you get as the output some norm of x, which you write with these bars. The norm of x is some number, some real number. And actually, it's a positive real number, or a non-negative real number. So it could be 0 or positive. And x is some element of your vector space. So it's a way of measuring the size of vectors in your vector space. And it must satisfy the axioms. Must satisfy the axioms. The norm of x equals 0. So when is the length of something sort of equal to 0? Well, that happens only if it's the 0 vector. X equals 0. So this is supposed to be an if and only if vector in the middle here.
This is what the norm has to satisfy?
These are the properties the norm have to satisfy for it to be a norm. Otherwise, it's sparkling lines. I don't know.
Not what the norm vector space has to satisfy.
Right. So
Vector space plus norm.
Right. Exactly. So a norm vector space has to satisfy all the things from the beginning about a vector space, plus the norm on it has to satisfy these three things. So these are the three properties. So that's one. So the norm is equal to 0 if and only if the vector is 0. The next thing is it has to play nice with scalars. So if you multiply lambda x and you ask what the norm of that is, it has to be lambda times the norm of x. So if you double a vector, you have to also double the norm of the vector. Again, it makes sense to think of it as a kind of measurement of the length of a vector, right? Of course, the vectors are these weird abstract things, but you want it to satisfy that. And last but not least is it has to satisfy triangle inequality. So this last one is triangle inequality. The length of the vector x plus y has to be less than or equal to the length of the vector x plus the length of the vector y. Okay. Those are the three properties it has to satisfy. That's a norm. Questions or comments about norms? This is another good place to think about. Maybe I'll set up a poll and I'll send it around to see what you guys think is better. But you saw me do the definition of the vector space with the typing, and then you saw me do the definition of the norm with the writing. You can decide which one you like better or worse, and let me know, and we can do that for the rest of the course. But today we'll do like a 50-50 mix, so you can get a feel for both. Okay, so that's a norm. What are these norms and where do they come from? Well, you guys hopefully took a course where you did a metric. And a metric is also an idea of doing distances. So what is the relationship between norms and metrics? And that is what I have for you in the next mathematics question to think about. So you've seen this thing is called triangle inequality. That's got something to do with the triangle inequality from the metric. But what exactly? And can I find what I'm looking for? Here it is. It's back. Okay. So how is the concept of a norm? So a norm is this thing we do the length of a vector related to the properties of a metric. So a metric is something where you do a distance between 2 points. So you have a norm is just one vector at a time, and a metric is 2 vectors at a time, and they both are measuring distance in a way, right? What are these two things? How are they related? And how do you think they are? And I gave some very vague options, but I really would just like you to spend a couple of minutes and think about what could the relationship be, and why did you take a whole course on metrics, and then all of a sudden we're doing norms? Like, why didn't we do metrics again? Okay, so take a couple of minutes, think, talk to your neighbors, and then we're going to take it up together and go from there. Okay, and I'll let you guys think which one is which. Okay, let's see what people said. Which way is it? Which one is a special case of the other one? And I phrase it in a kind of a vague way to keep it more understandable. So we got 8 people who think a norm is a special kind of metric and 3 people who think a metric is a special kind of norm. The majority is correct. A norm is a special kind of metric. And very specifically, let me tell you more specifically, a norm is something you put on a vector space, whereas a metric is something you put on a metric space. A metric space has no concept of being able to add and scalar multiply, whereas the vector space has addition and scalar multiplication. So I really think you should think of it as a norm is a metric, but it plays nicely with the addition and scalar multiplication. So a norm, you should think of it as a metric which respects, let's say respects, that's a good math word, respects the plus and scalar multiplication. Okay. And very specifically, how do you get, if you have a norm, how do you make a metric? You make the metric by saying the distance between x and y, that will be the norm between x minus y. So once you have a notion of subtraction, you can always find the distance between any two things by just subtracting them and then taking the norm of that particular thing. And you'll see that all the properties of metrics translate into the properties of norms if you have things set up in the right way. So for example, one of the rules for a metric is that the distance between x and x must be 0, and if the distance between two things is 0, those are the same thing. Well, that's exactly what this property over here is saying, right? So the difference, if x minus x, if the norm of that is 0, then it has to be the same thing. Hopefully that made sense. So all the properties of metrics that you guys have done in another course, they will carry over to the norm, and we're sort of like building on that and looking at these like specific types of metrics that respect the addition and scalar multiplication structure on the space. So they're like very special metrics that agree with the pluses and the times that we have. Yeah. Okay. Questions or comments about that one? I have a couple of true-false questions that will be on the homework. So there's a homework due like every 3 Fridays, and the next one, which is a week from this Friday, so like 2 weeks from now, we'll have some true-false questions about this norm to metric thing for you guys to play with. And then on the midterm, which is at some point in the course outline, I don't remember when exactly it is, but not for a while, I will give you one of those questions and you'll write out the full thing. So if you just guess true, false, you might get the homework points, but you won't get the midterm points. So that's coming up. Okay. Let's do an example. If everyone is satisfied, let's do an example. And the example I'm going to do is the LP norm. And that's going to be on R to the n, or let's put it on sequences. So remember, sequences are really like functions from the natural numbers to R. E.g., you could, if you were loved symbols, you would write this as R to the power n, like this, right? So R to the n is f from 1 to n to R, and R to the natural numbers are sequences. And both of them have an LP norm. What is the LP norm? Well, the LP norm is written like this. So if you want to know what is the LP norm, so you write P over here so people know you're talking about the LP norm, what you do is you take the absolute value of all the components. So you do x1 plus x2 plus ... all the way up to xn. And you take their absolute value and add them together. And then before you add them together, actually, you take all of them to the power p, and you take the whole thing to the power 1 over p for x in Rn. And if it's an infinite sequence, you just do the infinite sum. So let me write it out also as an infinite sum. I equals 1 to infinity of xi, absolute value, to the power p, to the power 1 over p. Okay, this is for x in, I'll write it like this, Rn. Okay. Of course, if you do an infinite sum, even if all the individual terms are finite, maybe that might be infinite. So the p norm of something might be infinite for the infinite sequences. Of course, it's always finite in Rn. Let's see what it looks like using my favorite math tool, Desmos. Okay. So here I have, in R2, I have an x and a y, and that is the formula for the p norm. And I said, please give me all the points whose p norm is less than 1. All the points whose p norm is less than 1. And here, p equals 2. When p equals 2, this is a set you should be very familiar with. This is just a circle. And that's because when p equals 2, this is the ordinary Euclidean length, right? So this formula, when p equals 2, is do the square of all the components, add them together, and then take the square root. That's the ordinary Euclidean norm. This is like how regular people measure vectors when p equals 2. When p is not 2, let's see what happens. So let's, the fun way, I guess, is to hit the play button, and it'll animate what happens. Do I want to go all the way down to 0? Let's do it. So here's p up to 5, looks like that, some kind of square. And then as you get smaller and smaller, you get some wonky thing like that. And what's going on is we're taking the individual terms to large powers. So like when p equals 5, you have something to the power 5 plus something to the power 5. If those things are very close to 1, that'll be a big number. It's very close to 1. And so that's why you end up with almost the entire square of things where both components are less than 1. On the other hand, if you make it a very small number, then we're taking like roots of these things. You get the kind of reverse effect. Okay, so that's the p norm. Question for you guys. Unless there's any questions or comments here, let's not open that. Questions or comments for you guys. My question is, which one of these is an actual norm? So I wrote down the formula, but it turns out that not all of these values are actual norms. So someone can write down lines like this, but it will not satisfy these axioms, always. So it only satisfies the axioms for certain values of p. And what I want you to do is look at this little picture, and I'll have it on animate for you. And I want you guys to stare at the picture and see what's going on, and try and see if you can guess for which values of p is it an actual norm, and for which values of p is it a non-norm. It will fail one of the axioms, at least, for some values of p. Okay, and I'll let you think about it. So take a few minutes, and I have some ranges, 1 to 2, p equals 1, p equals 2, between 0 and 1, and for p greater than 2. I want you to select all the ones where you think it is an actual norm, and the ones where it's not an actual norm, don't select those ones. Okay, and you should stare at this and use what you know about metrics to try to figure out when is it a norm and when is it not a norm. Okay, feel free to discuss, or if you want, you can ask me. I can look at specific values for you guys. Right now it's animating all of them, but I'm happy to pause the animation. Okay, let's do a timer here. I'll give you like 3 or 4 minutes. The other thing you can do is, I guess you know the exact formula, you could just play with some vectors and see if you can find some examples or counterexamples or whatever. Let's do 3 minutes to start. Okay, there's 20 seconds left, and 3 people have answered. So maybe you guys are stumped. But put in some guesses anyway, and I'll see how the votes are coming in, and then we will revote if needed, if things are scattered. Take some guesses and see where is this a norm, where is this not a norm. Okay, let's take a look. Oh, you must stop beeping. Okay. All right. Let's see what people said. Okay. So pretty all over the place. I really like that 8 people selected this one because this one is the one you can do analytically. So this is showing that people were actually getting a pen and paper out and really doing things. When p equals 1, let's do this one together. When p equals 1, then you have this, so the so-called 1 norm, the 1 norm, which is the absolute value of x1 plus the absolute value of x2. So it's the sum of the absolute values of the components. And we know that absolute value satisfies triangle inequality. We know that absolute value is like a metric on the real number line. This is basically like you have 2 different real number lines with this metric that you know, which is absolute value, and we're adding them together. And this one will definitely satisfy all the properties because absolute value does. So, for example, the crucial one of triangle inequality, if you do x plus y in 1 norm, that'll be the absolute value of x1 plus y1 plus the absolute value of x2 plus y2, and that will be less than or equal to x1 plus y1 plus x2 plus y2, which is equal to the norm of x plus the norm of y. So if the question was like, prove that one of these norms is a real norm, the 1 norm is the easiest one to do it for because it's kind of made of ones you already know. The other one that you should probably know is a real norm is the 2 norm, because the 2 norm is everybody's ordinary, this is the ordinary so-called Euclidean norm. And this one, again, it's more work. It's x1 squared plus x2 squared, and then you do the square root. It's more work to prove all these things, but is more familiar. And I guess 7 people chose that too. So that was the second most popular one. The other ones are a little bit scattered. About half the people said they were, half the people said they weren't. But actually, 0 to 1, p between 0 and 1, was the least popular. So most people said that one is not a norm. Only 3 people said it was. I'll reveal that is correct. So you guys actually did pretty good. So the one that was least popular is the one that's not a norm. All the other ones are norms. And I think there's something about this picture that happens between 0 and 1 that people clued in on. Does anyone want to say? What did they see? Why they chose? Yeah.
It kind of looks like the shape goes from being convex to not as it goes through 1.
Yeah, so right when you cross 1, and then you have a nice little diamond. Let's go exactly to 1. So that's a diamond, and the sides are straight lines. And as soon as you cross that thing, then they kind of bow in a little bit. And that is no longer convex. And no longer convex is actually saying something that triangle inequality is violated. So what I have plotted for you here is the unit ball according to the norm, right? It's the set of points whose distance from the origin is less than 1. The set of points whose norm is less than 1. And the unit ball must be convex because of triangle inequality. So the unit ball, so here is like I guess a little proposition. So let's say the ball centered at 0 of radius r, this is the set of all x such that the norm of x is less than r. This must be a convex set. Must be a convex set. And I can say because of triangle inequality for norm. So, oh, by the way, sometimes people, when we want to talk about the norm, just as a norm, we'll write norm dot, right? And so norm x means the norm of the vector x. Norm dot means I don't want to think of it for a specific vector x. I want to think of it as a norm. I guess it looks a little bit like a TIE fighter, which is cool. Okay, let's do the proof of this. What is the proof? What does convex mean? Convex means if x1 is in ball of 0. Actually, let's do x and y. So keep it separate. If x is there and y is there, then any combination, let's do lambda x plus 1 minus lambda y, is also in the ball. That's the definition of convex. If you have 2 points and you draw a line that connects them, the line segment connecting them, so lambda is in 0, 1, then that line segment must be in the ball. Actually, we can draw this in Desmos. So why don't we pick 2 points? Let's pick the point 1, 0, and let's pick the point 0, 1. So there's 2 points. And if you connect these two things, if you do t times, well, let me do this. Okay, let me do it this way. T times 1, 0. Will it let me do scalar multiplication? Let's find out. Plus 1 minus t. Otherwise, we can do it. I know how to do scalar multiplication. So we're going to be okay either way, guys. Don't fret. Okay, look, it lets me do it. So there's the point 1, 0. There's the point 0, 1. And there is the linear combination t times 1, 0 plus 1 minus t times 0, 1. And Desmos knows that t is a magical number. That means do all the things in between. So I called it lambda. Desmos calls it t. And you can see here, it's not convex, right? Because this green line does not lie in the ball. But for norms, it always is convex. And why is that true? If you do the norm of lambda x plus 1 minus lambda y, that's the point we care about. That's the point on the green line. And you do its norm, let's apply the rules for norm. Well, one of the rules for norm says that we can do triangle inequality. That's triangle inequality. Triangle inequality. And then we get the norm of lambda x plus the norm of 1 minus lambda x. Lambda is a number between 0 and 1, so it's positive. And one of the other rules for norms says that if you do the norm of lambda x, you get lambda times the norm of x. Okay, and this x magically was converted from a y. Let's put it back. Okay, lambda times the norm of x plus 1 minus lambda times the norm of y. So by triangle inequality, you can split them apart, and the norm of x and the norm of y are both known to be less than r because x and y are in the ball over here. So this is less than or equal to lambda times r plus 1 minus lambda times r, which is r. So if you have 2 points in the ball, and you do this line segment between them by the triangle inequality for norms, and just simple arithmetic of how norms play with scalars and addition, you get that the final point is also a norm less than r, and therefore in the ball. Okay, and so what this is saying is if you have a picture like this, it's definitely not a norm. It doesn't satisfy triangle inequality, because for norms, it must be a situation like that, and that one is a norm. So in fact, I think the converse is also true, but maybe a little trickier. I think if the ball is convex everywhere, then it's got to satisfy triangle inequality. Triangle inequality is somehow just saying that the ball is convex. Okay, so very nice. You can see from these pictures, as soon as you cross one, it's not convex. As you keep going bigger and bigger, it gets more and more convex, and it's quite nice. It always will be a norm. Questions or comments about that little demonstration? Okay, I'm going to say one more thing, is that one more fun thing happens. Let's go up to 1,000 here and see if you can spot the pattern. Okay, instead of animating back and forth, let's only animate forward. Let's do it, I don't know, in slow motion. Let's see what this looks like. Do you see what's happening as the p-value gets bigger and bigger and bigger? We're getting closer and closer to something. Yeah.
A square.
It's a square, yes. So this it starts out very rounded, right? And as the p-value gets bigger and bigger, you get closer and closer to a square. The square, the exact square, so you never actually reach a square. Of course, you get closer and closer to a square. The square itself is also a norm. And the square itself is known as the infinity norm. So let's go add this back in. There's one more that you should know, which is the infinity norm. And the infinity norm, instead of taking the numbers, taking them to the power p and then adding them together, what you do is you just look at the largest possible one. So it's the maximum of xi. Absolute value. That's it. So I going from 1 to n. If it's a vector in Rn, it's just the maximum. So I can also plot that over here. Let's do the maximum of the absolute value of x with the absolute value of y. If I plot that as less than 1, that is exactly a square. And so the red set approaches this purple set. And it turns out this one is also a norm. This is also known as the maximum norm. This is also a norm. Also a norm. And you can check and make sure that it satisfies triangle inequality because the square is convex. Okay. That's another good one to know. Okay. Okay, one more thing. I did not say it. I said it. I told you the result, but I didn't tell you mathematically why it's true. So why is this norm sub p a true norm for p greater than 1? There is a theorem called Minkowski's inequality. Minkowski's inequality. And what does it say? It says if you do x plus y norm p, that is less than the norm of x sub p plus the norm of y sub p. This is called Minkowski's inequality, and it requires proof, right? It's really a statement about sums of numbers to the power p. And it is in the textbook, so if you want to read it, you can read it. It's like 2 pages of quite technical inequality work to prove it. And it actually comes from, it's a corollary to something called Holder's inequality. Holder's inequality, which we might use later in the course. And so there's like an exact way to prove this, and you can do it, but really it's just saying that the p norm is an actual norm. It actually satisfies the triangle inequality, which is the hard one to prove, for p greater than 1, and that is crucially used inside the proof. Nothing will work if p is less than 1 because it won't be a norm at all. So that's called Minkowski's inequality, and if you want to look it up, it's theorem 1.2.8. Okay. So I've told you what vector spaces are, I've told you what norms are, and now we're going to use the norm to start to do things. But this is a good place to stop if there's any questions or comments about any of this stuff so far. Yeah?
Minkowski's is saying that that statement holds true exclusively for p greater than 1.
Yeah, that's right. So you fix any p greater than 1, and then this will hold for all x and y, where x and y are either vectors of length n or infinite sequences that go to infinity, and will still hold. Yeah. Yeah, and the proof is quite annoying. I was thinking about doing the proof, and I was like, this is just like a lot of inequality stuff. If you really want to know, go look at the book. Yeah. Okay. Okay, so we have our vector space, which is going to be a function space. That's why we actually care. We're going to learn about functions. We are putting on this vector space structure of addition and scalar multiplication. We have these norms that we're going to use, and we're going to use these things to talk about convergence. We're going to talk about convergence. So the next topic is convergence, and also known as limits, and so on. So if we have a vector space with a norm vector space, we can talk about what the limits are on this space. Okay. So what does it mean? So if xn is a sequence of vectors in some normed vector space V, let's say n going from 1 to infinity. Okay, people will get mad at me if I don't put the subset. Okay, so we have some sequence of vectors, and we have some final vector x, which is in V, right? So you can imagine like a sequence of functions or a sequence of sequences, right? I think this is like, it's always worth your time to take a minute and just remember like what the things are. Because right here I've drawn a sequence, but the objects themselves might be sequences, right? They're anything from those vector spaces. So it's like, I know you like sequences, so I put sequences in your sequences. Like you gotta really keep your head screwed on straight with like what is what, like what type of object is each thing, or it's really easy to just go crazy. So by this I mean each xn is in V, and I have a sequence x1, x2, x3. So it's like a sequence of functions or something like that. What does it mean for xn to converge to x? What does it mean for xn to converge to x? So you could write this as the limit as n goes to infinity of xn equals x, or you could equally well write xn arrow x. And this needs to have some kind of definition that we can check. So we have these things. If they were just real numbers, we would measure with the absolute value and use the epsilon delta definition from first year calculus. But they're not real numbers, they're vectors. So what are we going to use instead? We're going to use the norm. Okay? And this really is kind of like in your metric spaces class, it means, in metric spaces class, it means the distance, let me put this as like a little aside. Don't move my icon, oh my goodness. Okay. So in metric spaces class, what does this mean? Let's do a little aside. In metric spaces, what you would say is that the distance between xn and x goes to 0. So you would measure how far away is xn from x, and if they're getting closer and closer together, if the distance between these 2 points is going to 0, then you would say they converge. In norms, we take the norm of the difference. So this means the norm of xn minus x goes to 0. So if you measure things using the norm, then it'll go to 0. Another way to write that is to say the limit as n goes to infinity of xn minus x equals 0 either way. So the two vector objects, the sequence x1, x2, x3, is converging to the final limit x in the vector space V if the sequence of real numbers, which is their difference normed, that's a sequence of real numbers. If that goes down to 0, that's exactly what we mean. So this is the definition of convergence. And the whole point of this course is that we can take notions of convergence that we care about in real life, and we can figure out what norm to use to kind of like measure that. So the norm is like a measuring stick that is going to let us like measure the things we care about. And I think a great example is that example I showed last class with the step function and having a PDE converging to that. So what does it mean for the PDE to converge to the solution of the PDE and so on? What does it mean when we have these things? Well, we're going to measure it with these norms. We're going to find the right norms to look at so that we can make sense of what's going on. And we're going to use those to say things about functions we care about. So that's why we're doing all this stuff. And I'll give you 2 examples of convergences we might care about. So here are 2 types of convergence of functions. Okay, so here the vector space V, it's the vector space of functions. So I'm going to say f, and we're going to pick an omega. For concreteness, let's pick the interval 0, 1. That's a nice interval to work on. So functions 0, 1 to r. Let's even make them continuous. I don't know, such that f is continuous to make things a little bit easier for us. So we're looking at continuous functions. Here's convergence type 1, known as uniform convergence. Uniform convergence. So in uniform convergence, which I'm sure you've heard about before, a sequence fn will converge to f. Means, what does it mean? It means for all epsilon and for all x, there exists a capital N so that the absolute value of fn of x minus f of x is less than epsilon for all lowercase n bigger than n. So in English words, this means you tell me how close you want to be, and there is some number n so that you're close enough to the target function f for every single value of x all at once. And this is why it's called uniform convergence, is because, don't cross out uniform, highlight uniform. It's called uniform because it works for every single x simultaneously. So this value of n, one value of n covers you for every single possible value of x. I think I wrote these in the wrong order. Yeah, I definitely wrote these in the wrong order. Okay, let me, this is a good boo-boo to learn from. Don't write the for all x here. So for all epsilon, there exists an n, so that this holds true for every x in 0, 1. Okay, there we go. Now it's correct. Before it was horribly wrong. Okay, so you tell me epsilon, I find an n, and that n works for every single x at the same time. And that is why it's called uniform. It works for every single x at the same time. The one n value covers you. The thing I had written down before was actually pointwise convergence. And in pointwise convergence, so let's give these things names. Fn goes to f pointwise. That means, what does it mean? It means for all epsilon, and now it depends on x. So for all x, there exists n such that fn of x minus f of x less than epsilon for all n greater than n. So what is the difference? In uniform convergence, n depends on epsilon, and in pointwise convergence, n depends on epsilon and x. So there's a different n value for every single epsilon and for every single x, whereas in the uniform convergence, there's one value of n that works for all possible epsilons at once. So one of these is uniform and one of these is not. Let's draw a nice dotted line between them. And these are two notions of convergence that you care about. When you're trying to say approximate a function, how well did you approximate the function? Well, one way is to say I'm approximating it uniformly, and the other way is to say I'm approximating it pointwise, and those are two different things. Who's heard of these before? Just making sure. Okay. So it's okay if you're a little rusty. Hopefully the for alls and their exists are okay. So those are two types of convergence, and it turns out that of these two types of convergence, one of them has a nice norm that goes with it, and you can study with our norm vector spaces, and one of them you cannot. There is no norm that works for one of these. And I want you to think about what you know about these, and could you come up with a norm that would work? Okay? And so that's the next mathematized question. Tell me, which of these types of convergence has a norm that will do the same thing? So we have this idea of converging with a norm, using the norm as our meter stick to measure how things are converging. And if you pick the right norm, you can get one of these, but one of these is impossible to get to. And I want you to just guess which is which. So think a little bit about which one you could make into an actual norm. If you've seen it before, you might know. I'll give you a minute to think about that. Again, always feel free to talk to your neighbors. Okay, let's see what people said. And again, this is not the kind of thing you could fully prove in a minute or two, but you can kind of take a guess or go by memory. One person says pointwise convergence has a norm, but 9 people say uniform convergence has a norm, and that is the correct answer. So well done everyone. Does somebody know what the norm is? What is the norm that goes with uniform convergence? Yeah, go ahead.
Is it the Euclidean norm?
The Euclidean norm So what's the so I told you the Euclidean norm for sequences, but now we're talking about functions from 0, 1 to r. So the norm for uniform convergence, it's going to be a norm on convergence. It's a norm on functions from 0, 1 to r. And again, I just picked 0, 1 arbitrarily, but it could be any subset. So what is the, how do you want to do the, what's the norm, what's the Euclidean norm on functions like that? Because you can't just add up the components, there's infinitely many like values, f of 0, f of 0.1, f of 0.01.
Because I'm guessing it would be the,
Yeah.
because if you have two functions, you take the difference of the output.
Yeah. So you're thinking of you're doing the difference of the norm of f minus g, right? So that's the difference of the output. Which if you tell me what is the norm of some function h, then I'll put them h equals f minus g and it'll work. So when you're talking about norms, you just have to tell me the norm of one function, and that will automatically tell me the norm of the distance between two functions by taking the difference. So I just need to know the norm of one function. You can think of the norm as how far away are you from the 0 function. Right? So I have some function, I want to measure how far away is that function from 0. What would that be? Yeah?
Is it the integral of the square of the function over?
Yes, this is a fantastic guess. So one thing you can do, and this is what we talked about in the first class, is you can do you take the absolute value of the function, h of x squared dx, like this, and you integrate from 0 to 1. And if you did that as a difference, this would be f minus g. F of x minus g of x. Absolute value squared dx. So in this one, you take how big the function is. If you want to do just the norm of some function h, you take how big it is, you square it, and you integrate everywhere. There is one step you're missing, which is at the end, this is exactly what you have to do, but at the end you have to do one stupid button on your calculator. All right, I'll give you a hint, which is when we did the LP norm over here, what did we do? Yeah.
Do you square root?
Yeah, that's right, you square root it. So this thing, what you've written down is a norm, and it's going to be a very important norm in the course, which is you do the square root of all that. But this one is not for uniform convergence. This is called the 2 norm, and this is actually called the L2 norm. And that's going to be a big player in the rest of the course. But the L2 norm does not tell you about uniform convergence. How do I know it doesn't tell you about uniform convergence? Uniform convergence is the idea of getting close everywhere, right? So two functions converge uniformly if they get close to each other everywhere. But the L2 norm, because it's doing an integral, what happens is you can have a big problem. Like you can be off by 1,000 as long as you're only off by 1,000 on like a tiny, tiny interval. So if you have a spike like this function in the L2 norm is very close to 0 because that spike is really narrow. So even though it's very tall, because the spike is so narrow, the L2 norm of this is small. So the L2 norm of all this stuff is small, but that function in the uniform idea is quite far away from the 0 function because the spike is so tall. So the L2 norm is kind of like how much area is underneath the spike, whereas we want to know what is the tallest the spike could be. Did someone else have their hand up? Yeah.
The distance function?
Yeah, what is the distance function? So the norm, so this norm doesn't work for what we want. This is a norm for something else. The norm that we want is something different. And yeah, what do you want it to be? The absolute value of what? It's true, it is going to be an absolute value.
Of fx and gx.
Yes, okay. So if you do the absolute value f of x minus g of x, before we took the absolute value, we squared it, and then we integrated it. What do you want to do with it? Because so x is some number between 0 and 1. And I need to, like, what do I do with the x value here? Which x value are you looking at?
Everyone.
Yeah, how do I look everywhere? Yeah.
Is it the max?
The max, yes, the maximum. So the maximum of x in 0, 1. Okay, and this will work. So this is called the infinity norm, or the sup norm. Sometimes people write the sup instead of the max. Why is the maximum the same as the sup here? Because I said the functions were continuous. And because functions are continuous, they will always achieve their maximum by the extreme value function. So this thing is called the sup norm. If you do it on just one function, so if you do it just on some function h, it's the maximum x in 0, 1. And that would be just the maximum of h of x. And this measures, if you have a big spike, it measures the tallest possible spike, right? It measures how far away are you in the worst case possible spot. And this thing, turns out, is the norm for uniform convergence. So uniform convergence has this as its norm. How do I say that? Let's say fact, and this is a good exercise to prove. Fn converges to f uniformly. So what does uniformly mean? It's exactly the definition over here with the epsilon and the n, right? So for every epsilon, you can find a single n that works. If and only if Fn converges to f under the infinity norm. And by the way, converging under the infinity norm, we gave the definition before, which is that the difference between Fn and f in the infinity norm, that is a sequence, and that must go to 0 as a sequence in R. As, let's say, as numbers in R. Numbers in R. Okay. And it's not a complicated one. Oh, okay, I guess we're out of time. It's not a complicated proof to prove that. It's just pushing the definitions around. Okay, that was where we were going to stop. So I'll have it back up so you can copy if you want. But there is no more stuff. Okay. Yeah, let's stop there. So next class, we're going to see this difference between pointwise, the fact that uniform convergence and pointwise convergence are different, and one of them you can do with a norm is something to do with the fact that it's an infinite space. If you had a finitely many points, then pointwise convergence and uniform convergence would be the same thing. But when you have infinitely many, it's very different. And we're going to see more of that next class. Okay, so I'll stop there. And I will post some homework problems for you guys. So the full set will be posted sometime soon. I'll post the ones from today's class and last class, hopefully tomorrow. Okay, see you guys on Thursday, and take care. I can scroll down a little bit, yes.